Alright, today we're going to talk about measuring stuff. We will do this all year, but we need to cover some basics first. So let's talk about accuracy versus precision. What's the difference? Accuracy is how close your value is to the actual value. Precision is how repeatable your measurement is. Let me show you a few examples and then I'll look at an actual number example. The way people always view accuracy precision is with a bullseye. So look at your first bullseye here on the top left, right here. This would be low accuracy, low precision. If the bullseye is the actual value, what we want to get to, notice this guy's not very close, right? He's not very accurate. I'll come back to precision in a second. So look at the second one. This guy's got high accuracy, right? He's pretty good. His accuracy is very close to the bullseye. He's close to the actual value. Let's go down here to the third one. We have low accuracy. So this guy is not very close to the bullseye, right? And then over here we have the ultimate champ. Who's very, very accurate and, as we'll see, very precise. What's precision, on the other hand? Precision is how repeatable your measurement is, right? It may not be correct, it may not be close to the actual value, accuracy, but it's repeatable. So let's go through them again. This first guy is the worst, right? He has low accuracy, he's nowhere near the bullseye, and his darts aren't close together, right? They're not repeatable. Second guy over here has high accuracy. He's getting pretty close to the bullseye, but none of those darts, none of those arrows, whatever, are anywhere around each other. So that's low precision. And then this guy is, our third guy under here is very accurate, very precise. He puts all his arrows right close to each other, but they're nowhere close to the bullseye. And then again, this guy's the champion. He's precise and accurate. In the laboratory, we want to try to be as accurate as possible. We want to get as close to the actual value as possible, and we want to be precise, right? If we do multiple experiments, we want each one of those the data to come back very close to each other. That shows we are using good laboratory skills. So, accuracy versus precision. There you go. Moving on. Let's look a little bit and talk about measured numbers versus exact numbers. Two types of numbers, exact and measured. Exact numbers, I say, are infinitely important. What's that mean? Well, to put it a little bit easier, exact numbers are known exactly, right? Who would have guessed that? Known exactly, or defined. And we'll look at some examples of this in a second, but these are exact. They're very important. They're known exactly. They're defined numbers. Where a measured number, on the other hand, these are shockingly measured, right, with some type of a device, whether it be a ruler, a balance. There's all sorts of measuring devices out there, and we'll use a lot of those. So they're going to have some error in it, right? Have you ever measured something and gotten it wrong? Measured numbers have some type of error, whether it's human error or we'll see machine error, limitations in equipment. So let's look a little bit about exact numbers. And exact numbers obtained when you count objects or use a defined relationship. And again, I would say the key words there is a defined relationship. Counting objects are always exact. I can count 2 soccer balls. I can count 4 pizzas. And I'm going to be right. Here's the one we'll look at a lot in chemistry, is an exact relationship. 1 foot always equals 12 inches, right? 1 meter always equals 100 centimeters. That is an exact relationship. Very, very simple. So, for instance, a foot is not 12.000000001 inches. No, 1 foot is exactly 12 inches. So an exact number is either a counted number or it's a defined relationship, something that science has already deemed this is what a foot is, right? Okay, moving on. Measuring in science, when I'm talking about a measured number, the number tells a person how accurate the measurement is. I have some examples here. 43 centimeters tells me that the measurement is somewhere between 40 and 50 centimeters, right? Depending on what type of ruler we're using. Notice this, 43.0 centimeters tells me that the measurement is somewhere between 43 and 44 centimeters, right? That 0.0 tells a story. And we can go on. 43.00 tells me that the measurement is between 43.0 and 43.1. You should start seeing a little bit of a rule right here. And we'll see in a second that this digit is not for certain, right? 43.0 is for certain, but that extra 0 tells me something else. So what's the rule? Well, I just said it. The last digit of a measurement is always an estimate. Put a star by it. The last digit of a measurement is always an estimate. And I didn't say any number. I said a measurement. When you're measuring, whether it's a liquid, a solid, whether you're using a ruler or a balance, the last digit of a measurement, you're always going to estimate it. What's this look like? What would this measurement be? Well, we look at this ruler and what do we see? We see 0. These have marks, so we know that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Beautiful. Okay, so I see that piece of whatever. It looks like it's 1, 2, 3 something, right? So I know it's 3. I know it's not 4. I know it's between 3 and 4, so it's 3 point something. I can guess, but I can't be sure, right? So my last digit is what? It's going to be whatever I estimate it to. We are not sure of this digit. Now, we can look, it looks like it's pretty sure, but that's an estimate. That 0.2 is an estimate. It may not be exactly 0.2. We're sure of the 3, we're not sure of the 0.2, right? Okay, so what else here? And my picture didn't come up for that one, but that's okay. All right, so a few more examples here. Thermometers, we can do the same thing here. What do we see on our thermometer? What type of readings do we have? I have 20, I have 30, this would be 25, and it looks like each one of these is going to be 1. So this would be 21, 22, and go on, so on and so forth. So what would this first thermometer reading be? I see what? 26.6. Why? Here's 25. Here is 26. It's above 26, but is it to 27 yet? No, so we're going to have to estimate 26 point something. I said 6. Maybe you could have said 26.5. Whatever it is an estimate. Sure of the 20, sure of the 6, but I'm estimating the rest one. How about this next one? Take a second, pause the video, and see if you can get this one. So I see it's above 20, right? It's the same increments there. It's 30, maybe. We're sure it's 29, maybe it's 30, but it's certainly not above 30, so what would we say? Maybe 30.0, right? We're estimating that 0.0, that tenths place. It could be 30.1, maybe, probably not, or it could be 29.9. We just can't see real well. So that's a good way we estimate that last digit. All right, moving on. One more example. Graduated cylinder. One thing we'll talk about a lot with graduated cylinder is how to read it via the meniscus. I'll talk about that at a later time, but what do we have here? We have the measurement being 66.9. That last digit is an estimate, right? So we look here, we see that this is 60, this is 70, so 61, 2, 3, 4, 5, 6. 7. It's just below that 7 line, so 66.9 is probably a pretty good estimation of that last digit. So the last thing we'll talk about is significant digits. When we calculate, especially adding and subtracting, there's a simple rule. So we have a problem right here. It's pretty straightforward. We're just adding 26.2, 16.08, 3.007. So what do I see? This is rounded to the tenths place. This is rounded to the hundredths place, right? There's 2 decimal points. And this is rounded to the, there's an N in there, thousandths place, right? So how do I know what to round to? Well, it's really, really simple. We always round to the least number of decimal places. So I see here, this is the least number, 1 decimal spot or tenths. So 45.287 is going to turn into 45.3. That last digit is the one we are rounding to. We always are going to round to the least number of decimal places.